The European Southern Observatory is a 16-nation intergovernmental research organization for ground-based astronomy. Created in 1962, ESO has provided astronomers with state-of-the-art research facilities and access to the southern sky. The organization employs about 730 staff members and receives annual member state contributions of approximately €131 million. Its observatories are located in northern Chile. ESO has built and operated some of the largest and most technologically advanced telescopes. These include the New Technology Telescope, an early pioneer in the use of active optics, and the Very Large Telescope, which consists of 4 individual telescopes, each with a primary mirror 8.2 meters across, and 4 smaller auxiliary telescopes. The Atacama, a large millimeter array, observes the universe in the millimeter and sub-millimeter wavelength ranges, and is the world's largest ground-based astronomy project to date. It was completed in March 2013 in an international collaboration by Europe, North America, East Asia and Chile. Currently under construction is the European Extremely Large Telescope. It will use a 39.3-metre diameter segmented mirror, and become the world's largest optical reflecting telescope when operational in 2024. Its light-gathering power will allow detailed studies of planets around other stars, the first objects in the universe, supermassive black holes, and the nature and distribution of the dark matter and dark energy which dominate the universe. ESO's observing facilities have made astronomical discoveries and produced several astronomical catalogues. Its findings include the discovery of the most distant gamma-ray burst and evidence for a black hole at the center of the Milky Way. In 2004, the VLT allowed astronomers to obtain the first picture of an extrasolar planet orbiting a brown dwarf 173 light-years away. The high-accuracy radial velocity planet searcher instrument installed in another ESO telescope led to the discovery of extrasolar planets, including Gliese 581c, one of the smallest planets seen outside the Solar System. History. The idea that European astronomers should establish a common large observatory was broached by Walter Baade and Jan Oort at the Leiden Observatory, in the Netherlands in spring 1953. It was pursued by Oort, who gathered a group of astronomers in Leiden to consider it on June 21 that year. Immediately thereafter, the subject was further discussed at the Groningen Conference in the Netherlands. On January 26, 1954, an ESO declaration was signed by astronomers from 6 European countries expressing the wish that a joint European observatory be established in the Southern Hemisphere. At the time, all reflector telescopes with an aperture of 2 meters or more were located in the Northern Hemisphere. The decision to build the observatory in the Southern Hemisphere resulted from the necessity of observing the southern sky. Some research subjects were accessible only from the Southern Hemisphere, although it was initially planned to set up telescopes in South Africa. Tests from 1955 to 1963 demonstrated that a site in the Andes was preferable. On November 15, 1963, Chile was chosen as the site for ESO's observatory. The decision was preceded by the ESO Convention, signed 5 October 1962 by Belgium, Germany, France, the Netherlands and Sweden. Otto Heckmann was nominated as the organization's first Director General on 1 November 1962. A preliminary proposal for a convention of astronomy organizations in these 5 countries was drafted in 1954. Although some amendments were made, In the initial document, the convention proceeded slowly until 1960 when it was discussed during that year's committee meeting. The new draft was examined in detail, and a council member of CERN highlighted the need for a convention between governments. The convention and government involvement became pressing due to rapidly rising costs of site testing expeditions. The final 1962 version was largely adopted from the CERN convention, due to similarities between the organizations and the dual membership of some members. In 1966, the first ESO telescope at the Lisila site in Chile began operating. Because CERN had sophisticated instrumentation, the astronomy organization frequently turned to the nuclear research body for advice, and a collaborative agreement between ESO and CERN was signed. In 1970, several months later, ESO's telescope division moved into a CERN building in Geneva, and ESO's sky.The laboratory was established on CERN property. ESO's European departments moved into the new ESO headquarters in Garching, Germany in 1980. Member states' Chile and observation sites. Although ESO is headquartered in Germany, its telescopes and observatories are in northern Chile, where the organization operates advanced ground-based astronomical facilities. Lisila, which hosts the New Technology Telescope. Paranal, where the Very Large Telescope is located. Llano de Chajnumta, which hosts the Apex Submillimeter Telescope, and where Alma, the Atacama, a large millimeter, submillimeter array, is located. These are among the best locations for astronomical observations in the Southern Hemisphere. An ESO project is the European Extremely Large Telescope, a 40-meter class telescope based on a 5-mirror design, and the formerly planned Overwhelmingly Large Telescope. The EELT will be the largest optical near-infrared telescope in the world. ESO began its design in early 2006, and aimed to begin construction in 2012. Construction work at the EELT site started in June 2014. As decided by the ESO Council on 26 April 2010, a fourth site is to be home to EELT. Each year about 2,000 requests are made for the use of ESO telescopes, for 4 to 6 times more nights than are available. Observations made with these instruments appear in a number of peer-reviewed publications annually. In 2009, more than 650 reviewed papers based on ESO data were published. ESO telescopes generate larger amounts of data at a high rate, which are stored in a permanent archive facility at ESO headquarters. The archive contains more than 1.5 million images with a total volume of about 65 terabytes of data. Lisila, located in the southern Atacama Desert 600 kilometers north of Santiago de Chile at an altitude of 2,400 meters, is the home of ESO's original observation site. Like other observatories in the area, Lisila is far from sources of light pollution and has one of the darkest night skies on Earth. In Lisila, ESO operates 3 telescopes, a 3.6-METRE telescope, the New Technology Telescope, and the 2.2-METRE Max Planck ESO telescope. The observatory hosts visitor instruments attached to a telescope for the duration of an observational run and then removed. Lisila also hosts national telescopes, such as the 1.2-METRE Swiss and the 1.5-METRE Danish telescopes. About 300 reviewed publications annually are attributable to the work of the observatory. Discoveries made with Lisila telescopes include the HARPS spectrograph detection of the system around Gliese 581, which contains the first known rocky planet in a habitable zone outside the Solar System. Several telescopes at Lucilla played a role in linking gamma-ray bursts, the most energetic explosions in the universe since the Big Bang, with the explosions of massive stars. The ESO Lucilla Observatory also played a role in the study of supernova SN1987A. ESO 3.6-METRE telescope. The ESO 3.6-METRE telescope began operations in 1977. It has been upgraded, including the installation of a new secondary mirror. The conventionally designed horseshoe mount telescope was primarily used for infrared spectroscopy. It now hosts the HARP spectrograph, used in search of extrasolar planets and for astroseismology. The telescope was designed for very high long-term radial velocity accuracy. New Technology Telescope. The New Technology Telescope is an alt-azimuth, 3.58-meter Ritchie-Creation telescope, inaugurated in 1989 and the first in the world with a computer-controlled main mirror. The flexible mirror's shape is adjusted during observation to preserve optimal image quality. The secondary mirror position is also adjustable in 3 directions. This technology is now applied to all major telescopes, including the VLT and the future EELT. The design of the octagonal enclosure housing the NTT is innovative. The telescope dome is relatively small and ventilated by a system of flaps directing airflow smoothly across the mirror, reducing turbulence and resulting in sharper images. MPG ESO 2.2-METRE telescope. The 2.2-METRE telescope has been in operation at Lucilla since early 1984, and is on indefinite loan to ESO from the Max Planck Society. Telescope time is shared between MPG and ESO observing programs, while operation and maintenance of the telescope are ESO's responsibility. Its instrumentation includes a 67 million pixel wide field imager with a field of view as large as the full moon, which has taken many images of celestial objects. Other instruments use the Grand, which seeks the afterglow of gamma-ray bursts, the most powerful explosions in the universe, and the high-resolution spectrograph FEROS, used to make detailed studies of stars. Other telescopes. Lucilla also hosts several national and project telescopes not operated by ESO. Among them are the Swiss Euler telescope, the Danish National Telescope and the REM Trappist and Tarot telescopes. The Euler telescope is a 1.2-METRE telescope built and operated by the Geneva Observatory in Switzerland. It is used to conduct high-precision radial velocity measurements, primarily used in the search for large extrasolar planets in the southern celestial hemisphere. Its first discovery was a planet orbiting Gliese 86. Other observing programs focus on variable stars, astroseismology, gamma-ray bursts, monitoring active galactic nuclei and gravitational lenses. The 1.54-meter Danish National Telescope was built by Grub Parsons and has been in use at Lucilla since 1979. The telescope has an off-axis mount, and the optics are a Ritchie-Creation design. Because of the telescope's mount and limited space inside the dome, it has significant pointing restrictions. The Rapid Eye Mount Telescope is a small rapid reaction automatic telescope with a primary 60-centimeter mirror. The telescope, in an alt-azimuth mount, began operation in October 2002. The primary purpose of the telescope is to follow the afterglow of the GRBs detected by the Swift gamma-ray burst mission satellite. The Belgian TRAPPIST is a joint venture between the University of Liège and Geneva Observatory. The 0.60-meter telescope is specialized in comets, exoplanets, and was one of the few telescopes that observed a stellar occultation of the dwarf planet Eris, revealing that it may be smaller than Pluto. The Quick-Action Telescope for Transient Objects, TARO, is a very fast-moving optical robotic telescope able to observe a gamma-ray burst from its beginning. Satellites detecting GRB send signals to TARO, which can provide a sub-arc-second position to the astronomical community. Data from the TARO telescope is also useful in studying the evolution of GRBs, the physics of a fireball and its surrounding material. It is operated from the Haute-Provence Observatory in France. Paranal. The Paranal Observatory is located atop Cerro Paranal in the Atacama Desert in northern Chile. Cerro Paranal is a 2,635-meter high mountain about 120 kilometers south of Antofagasta and 12 kilometers from the Pacific coast. The observatory has 7 major telescopes operating in visible and infrared light. The 48.2-METRE telescopes of the Very Large Telescope, the 2.6-METRE VLT Survey Telescope and the 4.1-METRE Visible and Infrared Survey Telescope for astronomy. In addition, there are 4 1.8-METRE auxiliary telescopes forming an array used for interferometric observations. In March 2008, Paranal was the location for several scenes of the 22nd James Bond film, Quantum of Solace. Very Large Telescope. The main facility at Paranal is the VLT, which consists of 4 nearly identical 8.2-METRE unit telescopes, each hosting 2 or 3 instruments. These large telescopes can also work together in groups of 2 or 3 as a giant interferometer. The ESO Very Large Telescope interferometer allows astronomers to see details up to 25 times finer than those seen with the individual telescopes. The light beams are combined in the VLTI with a complex system of mirrors in underground tunnels, where the light paths must diverge less than 1/1000th of a millimeter over 100 meters. The VLTI can achieve an angular resolution of milliseconds, equivalent to the ability to see the headlights of a car on the moon. The first of the UTs had its first light in May 1998, and was offered to the astronomical community on the 1st of April 1999. The other telescopes followed suit in 1999 and 2000, making the VLT fully operational. 4 1.8-METRE auxiliary telescopes, installed between 2004 and 2007, have been added to the VLTI for accessibility when the UTs are used for other projects. Data from the VLT have led to the publication of an average of more than 1 peer-reviewed scientific paper per day. In 2007, almost 500 reviewed scientific papers were published based on VLT data. The VLT's scientific discoveries include imaging an extrasolar planet, tracking individual stars moving around the supermassive black hole at the center of the Milky Way and observing the afterglow of the furthest known gamma-ray burst. At the Paranal inauguration in March 1999, names of celestial objects in the Mapuche language were chosen to replace the technical designations of the 4 VLT unit telescopes. An essay contest was prior arranged for school children in the region concerning the meaning of these names, which attracted many entries dealing with the cultural heritage of ESO's host country. A 17-year-old adolescent from Chuquicamata, near Calama, submitted the winning essay and was awarded an amateur telescope during the inauguration. The 4-unit telescopes, UT-1, UT-2, UT-3 and UT-4, have since known as Antus, Kuan, Melipal, and Yepan, with the latter having been originally mistranslated as Sirius instead of Venus. Survey telescopes. Visible and infrared survey telescope for astronomy is housed on the peak adjacent to the one hosting the VLT, sharing observational conditions. VISTA's main mirror is 4.1 meters across, a highly curved mirror for its size and quality. Its deviations from a perfect surface are less than a few thousandths the thickness of a human hair, and its construction and polishing presented a challenge. VISTA was conceived and developed by a consortium of 18 universities in the United Kingdom led by Queen Mary, University of London, and it became an in-kind contribution to ESO as part of the UK's ratification agreement. The telescope's design and construction were managed by the Science and Technology Facilities Council's UK Astronomy Technology Centre. Provisional acceptance of VISTA was formally granted by ESO at the December 2009 ceremony at ESO headquarters in Garching, which was attended by representatives of Queen Mary, University of London and SDFC. Since then the telescope has been operated by ESO, capturing quality images since it began operation. The VLT survey telescope is a state-of-the-art 2.6-M ETRE telescope equipped with OmegaCam, a 268-megapixel CCD camera with a field of view 4 times the area of the full moon. It complements VISTA by surveying the sky in visible light. The VSD is the result of a joint venture between ESO and the Astronomical Observatory of Capodimonte, a research center at the Italian National Institute for Astrophysics INAF. The scientific goals of both surveys range from the nature of dark energy to assessing near-Earth objects. Teams of European astronomers will conduct the surveys. Some will cover most of the southern sky, while others will focus on smaller areas. VISTA and the VSD are expected to produce larger amounts of data. A single picture taken by VISTA has 67 megapixels, and images from OmegaCam will have 268 megapixels. The two survey telescopes will collect more data every night than all the other instruments on the VLT combined. The VSD and VISTA will produce more than 100 terabytes of data per year. Llano-Dichajn. Into the Llano-Dichajnumta is a 5,100-meter high plateau in the Atacama Desert, about 50 kilometers east of San Pedro de Atacama. The site is 750 meters higher than the Mauna Kea Observatory and 2,400 meters higher than the VLT in Cerro Paranal. It is dry and inhospitable to humans, but a good site for sub-millimeter astronomy, because water vapor molecules in Earth's atmosphere absorb and attenuate sub-millimeter radiation. A dry site is required for this type of radio astronomy. The telescopes are Atacama Cosmology Telescope, Atacama Pathfinder Experiment, Atacama a Large Millimeter Array, QU Imaging Experiment, Polar Bear, Apex and Alma are telescopes designed for millimeter and sub-millimeter astronomy. This type of astronomy is a relatively unexplored frontier, revealing a universe which cannot be seen in more familiar visible or infrared light and ideal for studying the cold universe. Light at these wavelengths shines from vast cold clouds in interstellar space at temperatures only a few tens of degrees above absolute zero. Astronomers use this light to study the chemical and physical conditions in these molecular clouds, the dense regions of gas and cosmic dust where new stars are being born. Seen in visible light, these regions of the universe are often dark and obscure due to dust. However, they shine brightly in the millimeter and submillimeter portions of the electromagnetic spectrum. This wavelength range is also ideal for studying some of the earliest galaxies in the universe, whose light has been redshifted into longer wavelengths from the expansion of the universe. Atacama Pathfinder Experiment. The Atacama Pathfinder Experiment telescope is operated by ESO in collaboration with the Max Planck Institute for Radio Astronomy in Bonn, Germany, and the Onsala Space Observatory in Onsala, Sweden. It is a 12-meter diameter telescope operating at millimeter and submillimeter wavelengths, the largest of its kind in the southern hemisphere. APEX is a precursor of ALMA, an astronomical interferometer which ESO and its international partners is building on the Chajnamd Plateau. APEX is based on a prototype ALMA antenna that is modified to be operated as single-dish radio telescope. Atacama, a large millimeter, submillimeter array. ALMA is an astronomical interferometer of innovative design, initially composed of 66 high-precision antennas and operating at wavelengths of 0.3 to 3.6 millimeters. Its main array will have 50 12-meter antennas acting as a single interferometer. An additional compact array of 4 12-meter and 12 7-meter antennas is also planned. The antennas can be arranged across the desert plateau over distances from 150 meters to 16 kilometers, which will give ALMA a variable zoom. The array will be able to probe the universe at millimeter and submillimeter wavelengths with unprecedented sensitivity and resolution, with vision up to 10 times sharper than the Hubble Space Telescope. These images will complement those made with the VLT interferometer. ALMA is a collaboration between East Asia, Europe, North America, and Chile. The scientific goals of ALMA include studying the origin and formation of stars, galaxies, and planets with observations of molecular gas and dust, studying distant galaxies towards the edge of the observable universe, and studying relic radiation from the Big Bang. A call for ALMA science proposals was issued on the 31st of March 2011, and early observations began on the 3rd of October.